Good morning everyone. We are going to use this class today to discuss the Hamming code. Alright, so Hamming code is basically used in detecting error in a transmitted code. That's its first function. And secondly, to correct the error in the transmitted code. Now before discussing about the Hamming code, it's important to talk about parity and its use in digital electronics. Now parity indicates if a binary number has an odd or an even number of ones. Okay, and as an example to parity, we have two numbers here. The first one is 1001. If we count the number of ones, you will see that there are two ones. Therefore, it has or exhibits even parity. While in the second example, you will see that there are three ones. Therefore, this exhibits odd parity. Now, we spoke about transmitted code in the explanation to the Hamming code. The transmitted code or the received code has two parts. Here, I have split them into two. The message bit is 1001 and the one which is shown in red is the parity bit. Together they make up the received code. So the received code was 11001, and what is the parity of this number? So if we look here, we have three ones, which means that it exhibits odd parity. Now we go on to see what is the first function of the Hamming code, which is to detect error in the received code. So we will do this with the example of a problem. The question here is to determine the single error correcting code for the BCD number 1001 using even parity. There are two things that we need to take from this question. First, we have a message which is 1001 and there are 4 bits in this message. 1, 2, 3 and 4. And secondly, we need to use even parity when solving this problem. So the first step is to find the number of parity bits. And to find the number of parity bits, we have a formula. It's 2 to the power p must be greater than or equal to m plus p plus 1. Let's take that as the first equation, where m is right. So the first step is to find the number of parity bits. And to find the number of parity bits, we use the formula 2 to the power p must be greater than or equal to m plus p plus 1, where m is the number of message bits. In our case, that is equal to 4 because our message is 1001. And p is the number of parity bits, which is what we need to determine. So we're going to use a trial and error method to determine the value of p. And p should be the first value that solves the equation 2 raised to p must be greater than m plus p plus 1. So let's substitute values for p. So as case 1, I'm going to say p is equal to 0 and m is equal to 4. And when I substitute that in this equation, I get 2 to the power 0 must be greater than or equal to 4 plus 0 plus 1, which is not true because 1 is not greater than or equal to 5. Now if we go on to the second case, where I substitute p equals 1 and m remains as 4, we get 2 to the power 1 must be greater than or equal to 4 plus 1 plus 1, which is again not true, as it is 2 is not greater than or equal to 6. Substituting p equals 2, which is case 3, we get 2 to the power 2 greater than or equal to 4 plus 2 plus 1, which means that 4 must be greater than or equal to 7, which again is not the case. Case number 4 has P at 3 and M equal to 4. And when you substitute that, you get 2 to the power 3 equal to 4 plus 3 plus 1. In other words, 8 is equal to 8. This is the first value that satisfies the equation 2 to the power P greater than or equal to M plus P plus 1. Hence, the value of P is 3. Okay, after determining the number of parity bits, we go on to step 2, which is to determine or construct the bit position table. So in order to construct the bit position table, we first need to determine the total number of bits. In our case, the total number of bits is equal to the total number of message bits plus the total number of parity bits. That is 4 plus the 3 that we found in step 1. So in total we have 7 bits. Now we are going to write those 7 bits in the bit position table. This is the bit position table. We have 5 rows here: the bit designation, the bit position, the binary position, the number of message bits, and the number of parity bits. So let's start by putting in the number of bits. So we have 7 bits in total. So they're going to be 1, 2, 3, 4, 5, 6, and 7. The next step that we do is to determine the binary position. So in order to get the binary position, we write each of this in 3-bit binary. So 0, 0, 1, which is binary for bit position 1, 0, 1, 0, which is binary for bit position 2, 0, 1, 1, which is binary for bit position 3, 1, 0, 0, which is binary for bit position 4, 1, 0, 1, which is binary for bit position 5, 1, 1, 0, which is bit position for binary 6, and 1, 1, 1, which is binary for bit position 7. After we have found the binary positions, we go on to determining the bit designation. We said that we have 4 message bits and 3 parity bits. Now it's time to determine where the message bits will be and where the parity bits will be. Now, the easiest way to designate the bits is by remembering this rule. The parity bits will occupy bit designations where the bit positions are the powers of 2. So, the parity bits will occupy the bit designations where the bit positions are powers of 2. That is 2 to the power 0, which is 1. So that will be P1. 2 to the power 2 to the power 1, which is 2. That will be P2. 2 to the power 2, which is 4, will give you P3. And if there are more parity bits, they will occupy bit positions 2 to the power 3, 2 to the power 4, and so on. So we have our 3 parity bits in their designated positions. Now the remaining will be our message bits. So this will be M1 for the first message bit, M2, M3, and M4. So in total we have 4 message bits and 3 parity bits. It's key to note that M1 will be our MSB and M4 will be our LSB. We can, in this step, determine and write down the message bit. Remember, our message was 1, 0, 0, and 1. So we have now partially completed the bit position table by filling the bit position, the bit position, the bit designation, and finally we put in the message bits. Now what remains is for us is to determine the parity bits. Right. So in the last step we constructed our bit position table, and we are now going to the next step where we are going to complete our parity bits. So let's start by completing P1. So P1 checks all the binary positions with a 1 at the LSB. So let's look at the binary positions, that's here, and let's look at all the binary positions that have a 1 at the LSB. So that will be bit position 1, bit position 3, bit position 5, and bit position 7. So P1 checks all binary positions with a 1 at the LSB. And we look at the binary position, we have a 1 at bit position 1, we have a 1 at the LSB in bit position 3, a 1 at the LSB in bit position 5, and a 1 at bit position binary position 7. Alright? So that's how we get this values of 1, 3, 5, and 7. So we are basically checking bit positions 1, 3, 5, and 7 for errors using this first check. Now if we look at the message bits, we will see that in bit positions 1, 3, 5, and 7 there are 2 1s. There is the 1 at bit position 3 and there is 1 at bit position 7. This means that we have even parity, and if we remember, our question requires us to have even parity. So we wanted even parity, and at bit position P1 we have even parity, and because we have even parity we can place a 0 at P1 to show that there is a parity match. So now we need to determine P2. Now P2 checks all the binary positions with a 1 at the second bit. So you'll see that there is a 1 at bit position 2, there's a 1 at bit position 3, then there's a bit position at binary position 6, and there is a 1 at the second bit at binary position 7. So we have 2, 3, 6, and 7 which checks for P2. And here again we'll see that there are 2 1s. There is 1 at bit position 3 and there is 1 at bit position 7. Again, it means that we have even parity, because remember the question requires us to do an even parity check. So because we have a parity match, we are going to again place a 0 at P2. Right, now we need to find P3. So to determine P3, we look at all the binary positions with a 1 at the MSB. So we have a 1 at bit position 4, a 1 at bit position 5, a 1 at bit position 6, and a 1 at bit position 7. Now if we count the number of 1s in the message bit at those positions, we will see that there is nothing at 4, there is nothing at 5, there is nothing at 6, there is just a single 1 at bit position 7. So we have an odd parity, and the question requires us to do an even parity check. In order to make it even, we place a 1 at P3. So now if we look again, we have a 1 at 4, nothing at 5, nothing at 6, and then nothing at 7, which means that we have 2 1s, therefore P3 is also even parity. Right, so let's just look at the question that was asked initially. The question was to determine the single error correcting code for a BCD number 1001 with even parity. Now the last step is to write down the resulting combined code. That is the combination of the message and parity bits written together. So the message 1001, when given the Hamming code, becomes, or using the Hamming code, becomes 0011 001. I think I need to do that last bit once more. So before looking at our final answer, let's look at the question once again. The question asked us to determine the single error correcting code for the BCD number 1001 with even parity. Now, as a last step, we bring down the message and parity bits together to get the resulting combined code, which is 0011 and this is how we use the Hamming code to detect the single error correcting code. The second part of the Hamming code is to determine the correct code, and this involves detecting where the error is on the bit position table and then correcting the code. So we'll do this with the example of another problem. The question here reads, a code was received as 001001. Now we need to do three things with this question. Firstly, check if the received code is correct. Secondly, if there is an error in the code, determine which bit has the error. And finally, determine the corrected code. Right. So the received code from the question was 001001, and we need to make sure that it's using even parity. That's what the question states. Right. So we need to check each of our parity bits to see if we have a good parity or a bad parity. So this is what we're going to do. Now, parity bit P1 checks bit positions 1, 3, 5 and 7. This is something that we understood from our initial study. Now if you look at bit positions 1, 3, 5 and 7, we see that we have 2 1s. The question requires us to do an even parity check. We have 2 1s, which means that we have good parity. And when you have a good parity, you put a 0, and P1 is always at the LSB. Then we go on to P2. P2 checks bit positions 2, 3, 6 and 7. And we see that we have 2 1s at bit positions 2, 3, 6 and 7, which is exactly what the question requires. So we have an even parity match, which means that we have good parity. And if it's good parity, then we place a 0 again. The last parity check is for P3, and it checks bit positions 4, 5, 6 and 7. Here we see that there is just a single 1 which is at bit position 7, which is not even, which means that we have a bad parity. And when we have a bad parity, we place a 1. Now P3 defines our MSB. So what this basically means is that we have an error at bit position 100, and that 100 is obtained from this cell. That means that we have an error at bit position 4, which basically means that it is a 0 at bit position 4 at this moment, and that is a mistake, and it is actually supposed to be a 1. Right. So now let's look at that question once again. The question says that we received a code 0010001 and we need to check if this correct code is correct using even parity. So the first question is check if the received code is correct. The answer is no. The correct code, in fact the code was wrong. Now if it was wrong, which bit is wrong? That is the second question. And we found out that it's bit 100 or bit 4 which was wrong. And the last question was what is the corrected code? The corrected code is 0011001. So it was this bit that was where the mistake was, and we have now corrected it, so this is the corrected code. So this is how we use the Hamming code for firstly detecting the error and secondly for correcting the error in a received code.